Hello. Let's see if the stream is working. We'll start shortly once I know it's working. Yeah, there we go. Cool. Sick. Okay, so where do we begin? Yesterday, we got the SAT working, separating Axis Theorem. If you don't remember, just look at the stream history, or if you don't care, it doesn't matter anyway. But we got the whole SAT working, and we're just going to spend the next hour or two porting it into C. And we'll start on that right now. Oh God, please. There we go. Okay, so it's going to be a long process. We're just going to basically do everything that we did in Desmos, but in C, and just draw every step of the way. We have a new function called OBB versus OBB. We can ignore the circle v OBB for now. That's a stretch goal. So we only care about OBB v OBB. I guess we can do equals false, return this, and then we'll just set it to true. Oh boy, my keyboard is disconnecting again. Wow, can you imagine that, people? That's amazing. This is going to be great. Yeah, let's just get right into it. So we have RB1 and RB2. I guess we'll just start with what we did last time. B1 pause equals RB1 pause, B2 pause. You know how it goes. B1 half extents. Just kind of shorten everything. B1A for the angle. Basically the same that we did in Desmos. B2A. I guess we can call this yeah. Does this all compile? Of course it doesn't. Why would it ever want to compile? Wow. Oh. It's a float. Okay. So we got the angles and the half extents. We're already drawing them. We didn't need to worry about that. We can get the vertices. We'll do B1 verts. We'll have 4 of them. And then we'll have like a rotated version, and no, we need to rotate them all. So that's going to mean that we're going to take maybe I can do like back to B1 VO. Just as a little test run, we'll do B1 pause.x plus RB1 B1 HE.x y. We're going to subtract them. And this is where the vertex would be if the box wasn't rotated, but now we need to start rotating it. And so, do like back to E1 BO rotation equals back to rotate. And then inside we'll do negative B, B1 HE.x, B1 HE.y with B1A as the rotation angle. And we're taking that as if it's around the origin, and then we're rotating it. And then we can add that to box 1 position. So let's jam this in. Do B1 pause plus this. We'll do that for every vertex. So we're going to go 0, 1, 2, 3. It's going to be positive x, negative y, positive x, positive y, positive y, negative x. Then we'll do the same for vec 2 verts, or box 2 verts. Change the angle. B2A, B2HE, B2HE. Ooh, I mistyped it. Okay, so now we'll just draw. Draw circle AA. Convert them all to screen. Vec 2. We want to visually debug every step of the way just to try and fix any issues as we encounter them. So I'll do like B1 verts screen. And we'll have 4 of them. Then we'll do the same thing. Oh my god, please. We'll do 2 screen. Comma, yeah, E1 verts, 1, 2, 3, keep that, then we'll do B2 verts to screen, that's everything. Frame buffer width. Yeah. E1 verts screen. Oh, please. Do the same for box 2 verts. We'll draw them as white. Missing a semicolon on this problem. Okay. Hey, look at that. Okay, so we're definitely drawing vertices correctly. Do I want to, yeah, I guess we should also test with rotation, so I'll just hook the slider up to, this will be kind of a hack, but we can do slider value. Move through all the entities. Yeah, and we'll just do RB angle equals the slider value times 2 times pi. Unexpected end of line. Oh, yeah. Okay, let's see if we can rotate it. Okay, cool. So we're rotating the OBB, and you can see the vertices still rotate correctly. So that's working. Let me comment that out real quick. Okay, we're drawing the vertices correctly. I think I'll just comment this out. Or we can do if 0. Little thing we can toggle on and off for when we want to debug it. The draw circle AA thing is just a little function that I have for software rendering with anti-aliasing, with alpha blending. You can figure it out yourself. You know, drawing a circle is very easy. From a point, you just fill in every pixel that's within a radius. And then for anti-aliasing, you just calculate a little border that you want to make fuzzy. If you don't know what to do, you can just ask ChatGPT to give you, you know, some basic C code for it. Or just get a little demo working in Desmos. Okay, so we have the vertices. Let's loop through them and generate the edges. We'll do vec2 B1 edges. This will be 4. We'll do the same thing. We'll do B1 verts 2 1 minus 0 1 2 3 0 2 3. So we're going to go from 0 to 1, 1 to 2, 2 to 3, and 3 to 0. Make sure that compiles. Missing a semicolon. Whoa, yeah, right there. We'll do the same for box 2. Now we're going to draw a line. Draw the lines to represent, why can't I like draw arrow? Yeah, sure, why not? Let's draw some arrows. This will be ridiculous. Okay. So I think we also want to convert these to screen, these to screen, do we? Yeah. We can do vec2 B1 edges screen, just to scale them to the screen. We'll do B1 edges 0 times 2 screen. We want to do 2 screen. B1 edges 0 game state world camera pause game state pixels to meter game state frame buffer height. Still haven't made this any less verbose, so I don't really want to. I don't even think I need to. Let's make sure that we're doing this right for box 1 and box 2 edges. I have a curly brace problem. State. Oh, that's because I'm using semicolons here when I need to be using commas because I'm initializing a bunch of them in an array. Okay. Now we'll do this. We'll draw an arrow. Camera position, pixels per meter, and we'll start at box 1 verts, 2, 3, to box 1 verts plus the edges, B1 edges, 0 through 3. And this should probably work. Hopefully it works. Yeah, cool, look at that. So we're just drawing an edge, a little arrow along each edge. So the bottom edge points right, The right edge points up, top edge points left, left edge points down. Cool. So that works. I guess we could do this for every single edge. So we'll do B2 edges here. And you can see that now around every single... I changed the lines from like little infinitely thin lines to thin oriented bounding boxes, so that we'll just do SAT like OBB versus OBB for literally everything, which should hopefully clean up some edge case issues that we're having. Yeah, cool. Okay, so we're drawing the edges correctly. What's next? B2 edges. We're gonna get the normals now. Or we're gonna take, do I have something like that where I do like perpendicular? Back to perp. Perpendicular, perp. Perpendicular. No, it doesn't matter. It's fine. Just do something ad hoc real quick. We'll do B1, Vec2, B1 normals. I have 4 of them, 1 for every edge, and we'll do normalize, Vec2. We're going to feed in a Vec2, and this will be the edge, so B1 edges 0.y, B1 edges 0.x. So the bottom edge is going from 0 to 2, so its vector is 2, 0. We want to take the normal of that, negative 2, 0, so it's pointing down. We'll make the y negative. That should work. And then we'll do 1, 2, 3. And then we'll do the same thing for box 2 normals. And then we'll also convert them to screen coordinates. Want to make sure that we're drawing everything correctly. B1 normals, screen. We'll do 2 screen. I'll just copy over this. B1 normals. 1, 2, 3. Same for box 2. We'll draw them all. 0. Let's comment this block out. Let's just wrap it. Let's just preempt this. That, and then we'll do draw arrow. Let's just copy this. So we also want the centers just to draw them more easily, and just do that real quick. We won't really need these, but box 1 center, box 1 edge centers for them. And that will be, we'll need to take the slope, so we'll take the edge, we'll take the start vertex, we'll add the edge to it and multiply the edge by half. So we'll do B1 verts, 0, plus B1 edges 0 times 0.5. Do that for 1 through 3, 0 through 3. Do the same thing for box 2. And we have the centers in world space. We'll need to convert them to screen as usual, so we'll do back to B1 edge centers screen for them. Again, we're not doing arbitrary polygons, we're just doing squares here. Convert them to the screen, B1 edge centers. And now we can draw them all. We'll do E1 edge centers. Make it screen. E1 edge center screen. Plus B1 edge, E1 normals screen. Do I need to, did I already convert the normals to the screen? B1 normal screen. Okay. Let's compile. Okay. So, 2, 3. I keep doing it. I keep pressing end when I want to press the right arrow key. Okay, let's see if this works. It's not working. Okay, that's great news. Doing something wrong. Definitely want to draw the arrows. You are stopping there. Let's just go to the center right here. It should be like, in world space, that's 8x, 5y. So the second edge center on box 1 should be, if the half extensor 1, it should be 9, 5. 9, 5, okay, that's good. Am I not converting them correctly to the screen? Okay. What are the normals then? Edge 1 should be edge 1, 0 should be 2, 0, which means that oh, I think I have it backwards. What did I set it to in Desmos? How do I do the perpendicular? It's Vy negative x. Oops. That might not solve the problem, but we'll see. We're just taking the perpendiculars backwards. Okay, Problem still not solved. -0, 1, 0, 0, 1, -1, 0. The normals look correct. Doing the edge centers correctly. 9, 5, 7, 4. Okay, the edge centers don't appear to be correct. No, they do. Yeah, they're correct. Edge center screen plus normal screen. Okay. Well, and the second thing that we're drawing to the mouse, we're drawing like the screen positions. So mousing over 9, 5 in world, which will give us in screen space 4, 2, 5, 2, 4, 5. That should be the center, B1 center edge 0. 9, 2, 2, 7, 8. B1 edge center screen. Okay, well, I don't think that's right. B1 edge center screen. Oh, I was looking at the wrong one. I want to be looking at 1. 424246. That appears to be right. And then if we draw a normal, that'll give us. Oh, I see. We're also converting the normals to screen space. Normal screen. Oh. Okay. Yeah, that's wrong. We don't want to be doing that for the normals. I didn't expect this to happen. So instead, what we want to be doing what'll happen if we just do, instead of all that, comment that out. Normals times game state pixels per meter. Still broken. Look at that. What could be wrong? Did I drag that around accidentally? Enter screen 35305. That looks right. Almost a screen. We're just debug visualizing this whole thing. This is a disaster. How did I draw those original arrows? Oh. I was just doing it wrong. Man, okay, I got it all mixed up in my head. So the draw arrow thing converts it implicitly to screen space. I don't need to do the conversion when I call draw arrow. I was mixing it up with another function. This is just a consequence when you don't standardize the API you're using. So we'll just do this real quick. Here we will do B1 edge centers, B1 edge centers, B1 normals. Okay, this should be right. Yes, okay. Yeah, okay, there was no problem. We just weren't calling the right function. Cool. Okay. So, let's comment out that. So we have the normals, we have the vertices, the edges, the normals. Now, I think we'll just start doing all the projections. Edge centers, normals. Yes, okay, so we'll start doing the projections. And I think we can just call it float box 1 to box 1y projections. And this will be E1 verts 0. Do the dot product, vec2 dot between that and the normals. B1 normals 0. 1, 2, 3. And the dot product is where you do a dot x times b dot x plus a dot y times b dot y. Just didn't know. And the box 1 normal, if it's not rotated, it'll be pointing down because the first edge that we take is the bottom edge. 2, 0. The normal is 0, negative 1. So we're comparing all the vertices against the y-axis. We'll do this for every single one. We'll do the x-axis next. And that'll be b normals 1. Just make sure it compiles. Braces around scalar initializer. Oh, oops. Okay. It's against x and y. B1, B1y, B1, B1x. Guess we can project the points. Why not? B2, B1y, B2, B1x. Yeah, okay. So we're going to need to do this, oops, quite a few more times. Compare all the vertices against the box 2 normals. B1, B2y, B1, B2x. And then we'll do this all for the box 2 vertex projections. Change all these to 2. Box 2, box 1y, box 2, box 1x, etc., etc. Now I guess we'll yeah, I mean, we might as well do all the projections too, so oh boy. I'll just test it for one axis for now. Oh, no, again, we don't need to convert to screen space if we're just going to draw arrows, so I'm going to do all those draw arrow functions again. Oh, but we do need the screen space projection, so I'll do like vec2, b1, b1x projection for them. And then to get that, we just multiply it. We dot product. We dot it with the normal vector again to get the position along the normal. Or we just multiply it. Yeah, we multiply it with that normal. And I think it should work. I guess we'll find out. We'll do b1 b1x times b1 normal is 0. Y. b1x 0. 3. Okay, and let's draw lines from those to the x-axis, the y-axis, I mean. E1 verts. Zero, 1, 2, 3. 2 b1 b1y projections. Okay. Interesting. Okay. Oh, we don't need to add them together. We don't need to add them. Okay. Cool. So what this means is that we're casting every single vertex of this box against the y-axis. And we can do the same for the x projections, x against normals 1, and then we'll do the same for its projections against box 2. B1, B2, y and x, B2. Yx, Yx. Oh. Okay. Draw 4 sets of arrows. And they should all overlap. 2, 3. One verts. X. 2x. 2y. Hey, look at that. Okay, so It's drawing many, many sets of arrows because we're comparing against many different boxes. And also, this line right here. Oh, dude, that's so cool. Okay, so we can also rotate them. And you can see that the lines shift to match up with the axis of this little OBB. So, it's looking like it does in Desmos. Isn't that cool? Isn't that neat? So, those are all drawing correctly. We can just disable those. We have all the projections. We're drawing them for the initial box at least. Okay. So now I think we start taking the minimums. And this is a lot of code. Still, it's probably way faster than drawing even one of our tiny circles in the software renderer. Like, rendering is going to be way more expensive than any SAT collision test we do, and we can always optimize this later. Blah, 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 blah. So we're taking the projections. These are all just the drawing functions to make sure that what we had in Desmos was correct. And now, here we are taking the minimums. So we can do the same thing. Take the float B1, B1X min. Take handmade min of B1, B1X 0. And then we can just nest this multiple times, where we take the minimum. Doesn't really matter the order between 0, 1, and 2, and 3. Just make sure that compiles. Okay. So this should work. We're just nesting it multiple times. It's going to get kind of messy. 0, 1, 2, 3. We'll do this for, oh dear. The Y's. It's 2, 2Y. 2Y, 2. B1, B1X, B1, B1Y, B1, B2X, B1, B2Y. Just make sure you don't have any typos. I like highlight it. You see a little orange line around all the other ones. So B1, Y, we can swap these. Okay. B1, B2X. Again, just being a little obsessive here because I make typos very easily, and we'll probably still have a few. So these are the minimums, and we're going to take the maximums. You could probably wrap this in loops, but I'm being rather lazy about the whole thing, and I'm just going to make it as verbose as possible. So we have the minimums and the maximums of the projections. Let me make sure that's everything. Nihan THBK. Hello. Hello, Nihan Nijan. What's up? How you doing? We're doing the separating axis theorem. We're converting all of our Desmos stuff to C. So we got the B1, B1X, B1, B1X max. Oh. Well, we're doing the Y and the X maxes. B1, B1, X min, and then the max. Y min and max. 1, 2, 3, 4, 5, 6, 7, 8. And then we're going to take 8 more of the mins and the maxes for the box 2 projections. Right? I'm not missing anything. It's like sets of 4 for every box. Yes. Yes, yes, yes. Okay. Oh god. My mouse is still having troubles. I can hardly sometimes, okay, well, of course when I'm streaming there's no problems, but like I try to highlight stretches and it doesn't work, and the mouse like thinks that I'm dragging something and it like releases when I don't actually mean to. It's hard to describe. Whatever, you don't care. Change all these to box 2. Oh, come on. Okay, let me just make sure that all these are correct. 2, 3, 4. Yeah, okay. Okay. So the next step is these are all like the one-dimensional projections along the axes, and now we're going to do that step where we take the maximum of the minimums minus the minimum. No, we take the minimum of the maximums, so you have like 2 lines here, right? We're going to take the maximum of the minimums, so it's going to be this one, and then we're going to take yeah, the minimum of the maximums. I'll draw it out again. Let me fill this. Okay. So here we have these 2 lines. They're overlapping. So I think it goes the maximum of the minimums. Just look. What is this? Oh yeah, okay. That's like the overlap along the axes, along every single axis. We take the minimum between the 2 maximums minus the maximum of the minimums. Min max minus max min. So these are the maximums. The minimum is going to be this one. Just highlight this. Minus min max maximum of the minimums. So these are the minimums. We're going to take this one. This is like 0, 1, 2, 3. Going to do 2 minus 1, so we have an overlap of 1. So what that means is that in this code, we're going to take the overlap. Float overlap along the box 1 x-axis, or the y-axis. We take the min of, oh Jesus, b1, b1, y min, or max, b2, b1, y max, minus handmade max, b1, b1, y min, b2, b1, y min. Make sure that compiles. Make sure that lines up with what we have in Desmos. b1, b1, y max, b2, b1, y max, b1, b1, y min, b2, b1, y min. Okay. That looks correct. Do that for the x-axis. And then for box 2 axes, change these to 2. 2. Okay. And now we'll just take the minimum of all of these. min overlap, standard min OB1Y, OB1X, OB2Y, OB2X. Close it? Yeah. Okay, so that should give us the minimum overlap, which means that I have like a little epsilon 0.0001, I don't know, whatever. If min overlap is greater than epsilon, it means that they are penetrating. Colliding. So I'll just set a breakpoint there. Yes, okay, so as soon as you saw, we dragged that box over, and as soon as they started connecting, we hit the breakpoint. Okay, that's great. That means that we are ostensibly working so far. How many lines of code are we at so far? We started at 2073. We're at 300 lines of code so far. Wowie zowie. Okay. So the next step. This is like, so we got to day one. Day one of the separating axis theorem when I was streaming it in Desmos. Now we're at the day two portion, where now we do the clipping. And now we'll need to, I mean, I guess we should probably still set it to, I don't know, what happens if we don't set the breakpoint and we like, okay, so nothing happens because we don't return any contact points. Okay, so we should still be able to draw everything. So, I guess might as well start. So we'll do best edge equals the overlap. Best edge index, sure, why not? Best edge index equals 0. And we'll just set up a bunch of if statements. We'll just get the sloppiest, most verbose thing working first, just to make sure that our logic is correct. That's all we care about. We don't need to be fancy. We don't need to optimize it yet. I suck at optimizing. I don't care about that. We just want to get it working. So we're just going to use a bunch of if statements. Nothing fancy. So if best edge index equals best edge equals, oh, okay, I see. If min overlap equals OB1Y, that means best edge index equals 1, 2, 3, 4. Else if min overlap X. Okay. I guess we'll need to set up the logic to start drawing all this. 1y, 1x, 2y, 2x. Okay. Got the best edge index. Now we're going to do the reference box. Int reference box. Best edge index equals 1. Reference box will equal 1. 2. Else if 1, 2, 3, 4, reference box will be 2. How long have we been streaming? Okay, almost going on an hour. Not bad. We're getting there. The axis. Okay. we going to get the axis. Vec2, the axis that we're separating along. We'll just null initialize it right now and do another conditional. Best edge index. Yeah. It's 1, 2, 3, 4. Axis will equal B1 normals 0, 1, 2 normals. Okay. Reference box position. Yeah, sure, why not? We'll do RB pause, reference box position equals, oh, this will be another thing. Do the same for instant box position. We'll just null initialize them. We'll do if reference box equals 1, do RB pause equals RB B1 pause, yeah. Was new, oh yeah, we can just wrap these in brackets and do the same for the incident box. IB pause equals pause. It'll just be the opposite of whatever the reference box is. And I guess we can, yeah, we'll just have pointers to the vertices and the edges and the normals. So we'll do vec2 to reference box verts, edges, normals, and do the same for the incident box for its edges and normals. Split this up into multiple lines because we're just going to set everything here. Okay, so if the reference box is 1, we're going to, oops. Okay. Hello, howdy. What is bro building? Are you on a treadmill? Yeah. No, it's not a pre-recorded video. I'm live. I am on a treadmill. We are doing the separating axis theorem in my 2D game engine. We already, you can see the previous streams where I do a little Desmos demo if you're not familiar with Desmos. And I also did a live stream where I constructed this whole separating axis theorem thing in Desmos just to prove how it works. And now we're porting that all into my game engine in C so I can have the separating axis theorem to pull apart colliding boxes in my little physics engine that I based off of Box 2D Lite. That's the full context for what we're doing. And we can detect if they're overlapping so far. Now we're doing the clipping step to determine which points of whatever box is penetrating the other box so we can pull them apart. So we can generate the point, the normal, and the separation that we want to plug into the impulse solver. The impulse solver is just every frame we're applying a velocity to the shapes to pull them out of each other. It's based on Box 2D Lite. You can see Box 2D Lite, the library for it over here. You can go to source. You can go to, I think it's the arbiter, and then pre-step, apply impulse. This is basically the code that I copied. I just made it data-oriented instead of object-oriented. And this is the impulse solver that we're using. But that's not what we're talking about right now. We're talking about the separating axis theorem. And where were we? We are trying to find the reference edges and the vertices, the edges, and the normals. So we're just going to set them equal to RB verts. If the reference box is 1, then the reference vertices will be RB1 verts. Same for edges and normals. Oops, box 1 verts. And the opposite for the incident vertices and all that stuff. We're just going to do the opposite in this little block. Where if the reference box is 2, there you go. Okay. I should be able to compile. That's compiling. What next? We have the reference box, we have the edges, we have the positions, the vertices, the normals. Now we want the collision normal. So we're going to do like vec2 collision normal equals, do like the difference between them. So vec2 diff equals IB pos minus RB pos. Then we'll do diff vec2 dot diff, and the axis, if it's greater than 0, if it's less than 0, do a little ternary operator here. And what's jammed in here? If it's less than 0, then we're going to flip the axis sign. Otherwise, it will just be regular axis. Okay. So we got that. Now we're going to pick the edges, the best edge. That's where we're going to need to start to debug draw everything again. The best edge is the most aligned normal axis of whatever edge. So here's what we'll do. We'll do float reference best edge, our best edge, equals the handmade maximum of every single one. So in parentheses, we'll do the collision normal, the dot product between the collision normal and the reference normals. Am I doing this right? Max. Okay, yeah. That. 1, 2, 3, 4. Yeah. Normals 3, 2. Okay, what's the problem? Got the parentheses all mixed up. It's still broken. Handmade max, vec2 dot. That. Man, I really these nested steps really confuse me. Just to make it easier on myself, I'll do oh man, reference normal 0 dot. I don't know. Whatever. Reference normal. Reference norm 0 dot product. We'll do this. problem with that. Oh. Oops. Let's rename these to, instead of reference box RB, let's just do I and R. Okay. 2, 3. It's going to be as verbose as possible. Make sure we don't break anything. Reference normal 0 dot. Do the handmade max again. Blah. This. Uncoding parentheses. Okay. 1 and 2 and 3. That compiles. Okay. Okay, it's compiling now. We'll do the same for the incident normals. Incident normal dot. And we'll need to flip the sign of the collision normal. And find the edge that most aligns with that. I best edge, I, okay, make sure that compiles, okay. So, we'll do best edge equals our norm. The reference normal dotted with the collision, that's what that means. If it's that, have int best edge, reference best edge index equals 0. Best edge index equals 1, 2, 3, 4. Do a thing called to our edge, I edge, have the vertices to RV1, RV2, IV1, IV2. I don't even know if we need to keep track of an index in here. That was just an artifact from Desmos. We'll keep going, and we'll do our edge equals reference edges 0, 1, 2, 3. Make RV1 equal to our verts 0, 1, 2, or 3. Make sure that compiles. Yes. And we'll just do RV2. Just set it in here, why not? RV2 equals RV1 plus our edge. I guess we can do that after we go through this whole block. Yeah. Okay. Do the same for the incident edges. I best edge index. Again, I don't know if we even need this, but whatever. I edge, incident edges, IV1, incident verts, I normal dot, best edge. And we'll do IV2 equals IV1 plus incident edge. Okay. So now we should be able to draw little arrows on the incident edges. So let's do that real quick. F1 and if we'll just draw them in white. Why not? Draw the reference edges in white. Or I have flux on, so it disables blue light. So we could like draw it in magenta, RGB. I'll do like 0. Why not? And we'll do reference vert, and then, oh yeah, RV2, yeah. And then we'll do the same in red for the incident. Okay. So when they collide, we should be able to draw, yeah, look at that. Okay, awesome. So, yes, 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 okay. Okay, cool. When they slightly overlap like this, we're drawing the correct edges, drawing them correctly in every orientation. So I am afraid this is working just right. Yeah. Yes. Yeah, let's compare it against other lines. Cool. Yeah. Don't know if I like that. Oh well. I guess we'll see how it responds when we get started with it. I don't like that. We're pushing out. The reference edge is magenta, so the reference edge will be I don't like this reaction. I feel like I'm doing something wrong. So I'm going to draw the normal. I'm going to draw the normals again. What am I drawing? Those are the vertices. These are the normals. Let's draw the normals. Okay. So the reference edge of the wall here has a normal pointing -1, 0. And that's most perpendicular with the square's second edge. I hot reloaded it, so when you hot reload in VS Code, it makes stepping into the debugger kind of tricky, so we'll just refresh it. Okay. Just want to debug this one thing or make sure that it's geometrically correct, because I expect instead of the bottom edge lighting up, we should be lighting up the right edge of the square to pull it out correctly, because that's the edge that most aligns. Oh, did I do I did it wrong. Yeah, okay. So instead of reference normals, I want to do I normals. That's easy. Easy mistake. And now, God, please. Okay, look at that. Okay, so when we collide, you see that the correct edge now lights up. So glad we debugged that. And it looks Much better now. Yeah. Yeah. Cool. Isn't that neat? So cool. Cool. Okay. So we're going in the right direction. Let me disable all that normal vector drawing. I'm glad that we set that up. That did pay off because we can verify that every step works along the way. I'll keep drawing the reference edges. So we have the correct edges now. Now we need to do the actual clipping part, where best edge, our vert, I best edge, I edge, I vert, RV1, RV2, IV1, IV2. We're getting there. Now we're going to clip everything. This might be sloppy. I guess we'll see. Maybe the Desmos, like the Desmos code right here, might be a bit loose. The code that we based it on in that little tutorial. It throws away vertices that are out of bounds, but I think we'll do the same too. So we'll do float. These are the projections of our edge. Back to dot our edge. RV1. RV2. D1 will equal, I think D1 is like, we set up the reference edges again. So D1 is down here, and again, we're projecting the vertices, the incident vertices, along the edge at the start of RV1. And determining if one is on the other side, and then we clip it. That's kind of what D1, D2 means. Vec2 dot our edge, IV1 minus O1 to float U1 equals E1 over D1 minus D2. And then we're going to use this to determine the clip positions. And this might take me a while because I always forget this step. D1 is greater than or equal to 0. Vec2, clip 1, this is IV1. Probably foreshorten it here. If D1 is greater than or equal to 0, we're going to use IV1. Else, clipped 1 equals IV2. And then take like the final one. Vec2, clipped 1. I don't know, clipped 11, clipped 1, 1. Where we'll do, if they're both greater than, yes. Okay. Clip 1, 1, clip 1, 2. D1 greater than or equal to 0, and D2 is greater than or equal to 0. Clip 1, 2. It's going to equal IV1 else 1, 2, is going to equal that thing, IV1 plus incident edge times U1. And we'll do, just draw them, clip 1, screen equals 2 screen. Just copy all this bullshit. Clip 2 screen. And we'll draw them in red. Can we draw them in red? Oh, yeah. Okay. Draw a circle, AA. One screen. Okay. Okay. Cool. You're drawing one of them at least now. Let's set up the other one. Oh yeah, this little thing right here. I was just experimenting with like rotating some lines around a little like star or a sun. It's just a little like shader thing that I made out of drawing like a circle and a bunch of lines that I apply a random value to every frame. So we're drawing the first clip point. Now we'll do the second one. Do float D12 or D21 equals vec2 dot negative R edge and clip 1, 1 minus negative O2 Can we do minus minus O2? Wrap it in parentheses. Yeah. Okay. R edge. Okay. And then float U2 equals D21 divided by D21 minus D22. And we'll do the same logic here. D2, D21. I only need one clip position here. D21 is greater than 0. Clipped, set clip 2 equal to clipped 11, clip 1, 1. Otherwise, set it equal to IV2 plus all that stuff. Okay, we'll draw these again. Give us both the clip positions. It's not right. I need to debug this. It's kind of right. Sometimes it's right. Guess we can also draw the text. tricky to get right. Treadmill turned off. CP1 and CP2. Our test 32. We're drawing them to the same position. You can see the one and the two overlap each other. That's why. Okay. Why would we be doing that? We're almost there. Of course, the last step is going to be the hardest. I'm drawing a blank now. Gonna need to debug it. I guess we can step through it. Good. How can we do this? I guess we can set it up exactly the same as we would in Desmos to figure out where we went wrong. Is it like a simple typo somewhere? Why does Desmos jump around like that? Yeah, I guess what we could do, let's just set it up exactly like this. Box 1, like box 2, C, CP1, CP2, okay. Okay, let's see if we can do this. I guess we can shift them to like 7.5 to 8.6. Oh, oops. Just plug in a case exactly like Desmos. Then we'll go to reinitialize all of our entities. Will be the entity. This one starts at 7.5. This one 8.6. They have the same half extents. We're drawing them at different colors. Okay. Okay. Interesting. They have different reference edges. Let's figure out where it goes wrong. Yeah, I'll just step into it. Yeah, this is the only intersection happening. Let's step into it and figure out how we select the reference edges. The reference box. Get rid of all this stuff. RB pause. Okay. Best edge indexed. Did we do this too soon? Reference box. Reference box is okay. Okay. So the reference box is 7.5. The incident box is 8.5. That's good. That's a good sign. Matches up with what we have in Desmos. Reference edges, vertices, normals. That should all be good. Let's figure out what my edge is. Reference edge best index. We think that it's 2. Instead of 0, 1, 2. Yeah, okay. That means that the reference edge is no, that's not right. It should be 3. What is the collision normal? Collision normal is 1, 0. Okay, so the collision normal is wrong. What's the difference between these two? Oh god. 1, 1. Yeah, difference is 1, 1. That's right. The axis is 1, -0. 0, -1. We choose the axis. Best edge index. It's 1, 2. 0.00477. 429. Yeah, I guess that can also work. Yeah, it's just a little, it comes down to floating point representation in C. I think Desmos uses doubles. So that is all correct. Because they like perfectly overlap, so we could choose either the x or the y axis, and it comes down to very subtle differences in floating point calculation. But I'm confused by the clipping. Let's take another look at it. Paint. This is the reference edge. R. This is the incident. It's I. This is at 7.5. This is at 8.6. 7, 8, 9. Well, no, this is at 7.7. That's the first clip point. But we're not clipping it to the reference edge correctly, so that's wrong. Stuff in here. Clip 1, 1. Clip 1, 2. Okay. So they're both greater than the bottom. Yeah. Okay, yeah, so that is IV1 right up there. That is the first incident vertex. And D1 and D2 are greater than 0, so we're going to store that. And then we're going to clip to the other side, or D1, 2. Clip 1, 2 is going to equal IV1 as well. Make sure that it lines up with the Desmos logic. This is going to take a while, sorry people. Yeah, oops. Simple typo. Should be IV2. Let's recompile it, see what happens. Okay. Okay, so CP1, CP2. Okay, we're getting closer. We just weren't feeding in the correct position for the second clip point. Clipping them, and then CP1, 2. Clip point 2. And then we're going to make sure they're within the reference edge normal. But they will be. Clip 111. Oh, okay, I think I'm just, yeah. Okay, so you see how we're drawing 3 points here. We're drawing 3 points here. I'm drawing CP1, but I don't want to, because that's been clipped. So instead of that, we'll just use the final clip position. So we'll do clip 2, 2. Do like clipped 1, clip 1, 2. How about that? And then instead of those, yeah, okay, so now you can see, yes. Okay, so we're drawing the correct clipped positions. That was just a little typo. It was my bad. Let's just make sure that they're all in the correct places. Yes. Isn't that neat? And then the final step is we want to make sure it's within that edge, the reference edge. So we'll hold off on drawing these until the very end. Flip to screen. Back to clip one final. And we will only draw it if, now we need to have logic where we like just discard them. And I also need to make sure that they're rotating correctly, all that stuff. Yeah, this is going to get tricky. I'll just need to debug. I'll need to test all the different cases. We're getting there. We do angle equals, what even define angle? That'll be angle equals pi times 0.5. We'll just give one of the boxes a little, why don't you like that? Oh, oops. Oh, was I doing that wrong? Oh yeah, okay. I was just rotating it, but it's still axis aligned due to that little rotation. You're rotating it by 90 degrees there. Okay. Okay. So we're correctly clipping both the points, but now we want to set up the logic where we check if it's within the reference edge. And if it is, then we store that contact, and if not, we skip it. So we're going to do, I don't know, bool cp1 within equals vec2 dot cp clip 1 2 clip 1 2 minus rv2 rv1. This is the half space test. You take any point, and then like you have a line. You take any point on that line. You take a point, subtract it with a point on that line, and then you dot it with the normal of that line. And so we'll do it with the collision normal. It's less than 0. It's within. Same for 2. 2 2. And now we'll do CP1 within if CP2 within, and then we'll draw them. It's clip 1, clip 2. Also include that. define the char outside as well as the int. Please. On this keyboard, I keep hitting end instead of one of the arrow keys that I actually want. X start, Y start. Oops. Okay. Now we should only draw them if they fall inside that edge. Yeah. Okay. Look at that. It appears to be working. Pretty cool. So now, I think we can just plug these in. So now we just need, we have the normal, we have the contact point. Now we just need, oh God, what did I do there? Yeah. Now we just need the separation, and we can get that with yeah, okay, here's what we'll do. We'll go to like what's like a functioning thing? Separation. Let's just pull it out of one of our existing functions. We'll do, yeah, whatever. Okay, just to start jamming it in. Still the contact stuff. I had it for OBBB line, static resolution. This is what we did on an earlier stream, and this is where we did the contact stuff. Yeah. And then we add it back. Okay. Okay, we're getting there. Bear with me, people. A and B. Okay, this could be tricky. I think A will be the reference and B will be the incident, so we'll also need to store pointers to the rigid bodies. So we can do, yeah. Yes. Rigid body RB equals null and incident body. Okay. The reference body will equal RB1. Incident body will equal RB2. And then in the other case, they'll be swapped. This is just setting up the information that I want to pass into the contact information. Reference body, incident body, contact, OBB, OBV. And the normal will be the collision normal. This will be RB, IV. I don't think we need that. We already did that. Change this all to, oh Jesus, that is not what I wanted. I never use that feature in VS Code and I don't know how to disable it. Entity B is -1. Do we want to do that? No. No, that's an artifact that we don't need anymore. Don't need the type, static penetration. We don't care about that anymore. The penetration will be, I mean, we don't even care about penetration anymore, but I guess we could do here's what we'll do. This will be the penetration. CP1 penetration, CP2 penetration. Then we'll just plug these in. The separation do that. Point is point. Click 1, 2. We don't care about local contacts. Yeah, sure, we can do friction. Oops. RB1, RB2. So we have the normal, the point, the separation. I think that's everything we need, and then we'll do the same here. Two. And we need to store these, or we'll do, just go back to OBBV line and figure out what we do there. Yeah. Okay, then we store it like this. Okay, and I guess we'll see what happens. It'll either be catastrophic or it'll start to work. Inertia, inertia. Okay. Hey, it I think we got the normal backwards. Okay. Okay, it's definitely backwards. I'm just going to go out on a limb and say that we need to flip the normals. Okay. Wow, that is freaky. Huh. Okay. Well, we have something working, and now we need to start debugging that. So we can go into the snapshot playback system. Okay. Interesting. Why is that? We should have clipped that point. Let's click it and see what happens. Won't be none. We're nearly there, just a few more problems with it. Can I go into the collision inspector? That is so weird. That's freaky. Man. Why did this stop working all of a sudden? I somehow swapped them? 1, 2. Wow. Wow. Okay. I don't like how it jumps there. Does it depend on which body you want to store? Wow. I really don't want to say that it's working, but God, it's been so hard. It's been so hard to get this far, but I think it might actually be working. My God. Oh my God. Please. Oh Jesus. My heart is pumping, dude. I want to believe so bad. That's crazy. Yes. Stacking appears to be a little unstable. And I think we need warm starting for that. Or, maybe that's just friction? God, that's so cool. That's so cool. Yeah, so you can see that they kind of slide up. I'll need to inspect that. I think we might need to add warm starting. I don't know what that means. That's something that we'll figure out in time. I think it's working. Wow. That is insane. Well, I think that's the separating axis theorem for you. We got it working in C in 2 dimensions for just little squares. We can go one step further. Why not? Let's add. The only other thing we would need to add is circles. Circle v circle. Because ultimately we're just going to have circles, squares, and capsules. And capsules can be composed into circles and squares. So we can just add the other thing right now. I did it this morning, and this is so amazing. Sorry, I'm just getting distracted. That's so cool. I wish I understood why stacking is unstable. You can see them kind of moving over. Are they sliding apart? Interesting. I guess I'll figure that out in time. It doesn't need to be perfect right now. That's so cool. That's so cool, bro. Okay. That's incredible. I didn't know I could actually accomplish that today. But we got it. So the next step, how many lines is that anyway? This is we started at like 2075, so this is like 500 lines. Yeah. Our OBV function, I mean, of course, we add a lot of verbose stuff. We can condense this probably in half. But it's 500 lines of code. Look at that. Okay. So the only other thing I would want to add is circle versus RBV. And this morning, just for fun, just to see if I had the mental model locked down, I added OBV versus circle. So you can see that when we move the circle around, we correctly resolve where it should be. And then I'll just show you what happens when we rotate this. Where do we rotate the box angle? Okay, yeah, so you see that no matter where the circle is, like even if the box is rotated, we're still resolving correctly. And that's because we're doing that same thing that I showed you in the circle v line thing, where we're just drawing where the circle is relative to the axis aligned box. We're like inverse rotating it. And then we're doing a few calculations on it, and we can set that up right here. Why not? We'll do vec2 bpos equals, we have circle RB and OBVRB. OBVRB pos vec2 BHE equals OBVRB half extents. We'll do float BA equals OBVRB angle. Vec2 cpos equals circ RB. Pos we'll do float radius equals circ RB radius. Circ RB. Circle RB. Let me add in a circle. I don't think we need to have either of these OBVs for now. Just have a few circles. Okay, so we have that in the radius. Let's do vec2 circle centered, and that'll be vec2 to inverse rotate cpos minus bpos BA. And that will be the circle at the origin. We can do the same for, like, bpos at the origin is just 0, 0. AC, BB. Okay, and then we're going to need to clamp it. Clamp. To clamp. Do I have a function like that? Clamp. Clamp. Okay. Yeah, let's just do floating point clamp. Get the back to circle centered clamp. CCC. Why not? Who cares? Circle centered clamped. CCC. CCC. And we are clamping the circle center to the negative BH half extents to positive BH at half extents. And now we're going to see if it's inside. That'll give us a different case. I'll do circle inside if cc.x is greater than or equal to negative BH extents and cc.y is greater than or equal to negative BHE.y and cc.x is less than or equal to BHE.x and cc.y is less than or equal to BHE.y. That will equal, we can just do circle inside equals that. Cool. Okay, so that'll tell us if the circle is inside the square. And then we'll take the axis that we want to resolve in, and that will be, yes, the absolute value in x equals fabs cc.x minus negative bhe.x. Axis negative x, axis positive x, axis negative y, axis positive y. Minus negative BHE minus BHE. Y. Y. Then we'll take min separating axis and made min of all this stuff over and over and over. ANX, APX, ANY, APY. And sep axis equals ANX APX Y P do the collision normal. Okay, how about this? We'll do back to collision normal. Then if the circle is inside, circle inside and this, and we'll do the collision normal equals like something that we specify. So if the circle is inside the AABB and it's closest to the negative x-axis, then we're going to resolve in the -1 direction. Otherwise, it'll be the +1 direction. -1, +1. Okay. Okay. And then if it's not inside, circle is not inside, we will just take the normalized direction from the circle center minus the circle center clamp position. That'll be the collision normal. Okay, and now we'll do vec2 diff equals CCC minus CC. The circle center clamp minus the circle centered. Float distance squared will equal vec2 dot diff dist equals fast square root f of distance squared. If distance is less than penetration inside, I guess we could do that too. Yes. We'll just do float extra penetration equals, is the circle inside, we'll take the min sep axis, otherwise we'll do 0, just to add some additional penetration resolution to it. Then penetration will be, am I doing this right? I always mess up this part. If the distance is less than, yeah, the radius. And that means we have a contact. So we'll do equals contact OBB circle equal collision equals false, collision equals true. I don't think that's right. OBB circle. Contact OBB circle. Ooh, I need to add that to the switch statement, as usual. Please. Everything that I need. Circle RB, OBB RB. Penetration is, do right here. Penetration equals the radius plus the extra penetration if we're inside minus the distance. And for separation, we just make it the negative penetration. The point will be the clamped circle position. Clamped circle. Circle center clamped. Okay. I think that should be everything. Let's see if it works. Hey, look at that. That is crazy. Okay. So now we also have circle versus oriented bounding box. So let's just add all of them together. Let's add another circle. Is this a circle? Where is the type? Am I not specifying a type? RB type. Circle. Okay, oops. Let's add in 2 circles and 2 oriented bounding boxes. And let's see if they play nice together. Okay. I'm not resolving Am I resolving collisions? I am resolving collisions between circles, but... Oh, okay. It's just for static resolutions only. So... that is interesting. Getting sucked into each other. Huh. Okay. How long have we been going? We're over 2 hours. I think this is the longest I've streamed yet. I guess we can debug it a little bit, figure out what's wrong. Turn on the treadmill again. Again, all we care about is circles and OBDs. We can make capsules out of them. We can compose a capsule resolution by just stacking together a bunch of collision tests between circles and oriented bounding boxes. I guess I should look at circle v circle and see what's wrong there. Let's go to the collision inspector. Pull these out of the way. Okay. What's even the problem exactly? Here's body update physics. Oh, I think that's the wrong one. I can never remember. Physics impulse update. Circle. OBB versus circle. And then if it's a circle, want to do circle v OBB penetration resolution. Oh, here we go. Oh. Separation equals penetration. I really should have combined all this by now, but we need to update this in three different places, so it's not ideal. Physics collision inspector. Just see if okay. Okay, so I want to reverse that contact normal between them. In the... that's a collision inspector. Oh god. This is just a little hack job. I can clean it up later. Okay. The circles now push off each other cleanly. Yeah. And now we just need to figure out why they don't resolve well against the dynamic bounding boxes. I guess we should draw more of that information. Wow. Perpetual motion machine. I'm still absolutely thrilled that we managed to actually get the the separating axis theorem working, even if stacking is unstable. I'll disable all the walls, and I'll only have one other OBB entity and one circle entity. Ah, I think that's the problem. I just, I just don't have the correct contact point between them. Why is that only a problem when it comes to OBBB, OBB? Strange. Inspector. Oh. I think we need to rotate the normal back. Back to rotate vision normal with PA. Then I think the separation, the penetration, everything else is the same. Oh, and the contact point is that's going to be a point on the axis aligned bounding box. So if we look right here, it's going to be a point right there. So what we need to do is we need to rotate that by the orientation of the box. So we'll do vec2 rotate that with BA plus the position of the box. That'll give us the correct point, penetration, and the normal. And I think yes, okay. So you can see that they should be resolving correctly now. And now I guess we'll just add everything else back in. Yeah, cool. Cool. Let's add in more entities. Instead of full screen here, I accidentally exited out. Okay, so they explode apart because they all start really close together. Let's see what happens. Interesting. Okay. Well, I'll say that it's working, and I could add. What's stopping us from adding a few more? It's going to get really messy. Let's add one at like 9. make this entity 11. Let's add another one, entity 12. My goat is streaming once again. Yo, what's up, John? We just got the separating axis theorem working, as well as OBB versus circle resolution. Oh, these are all going to start at the same position. Let me put one. Yeah, okay. They're all going to overlap and explode apart. Yeah, okay, let's see what happens here. Okay. Cool. It's really laggy when I zoom in. Okay, I mean, I guess that's not so bad. It'll jitter over time when you stack them. Let's try and set it up in the middle and then like roll a ball into it. That's cool. Bye-bye. All gone. Oh, the arrows appearing wherever contact is made of the objects. Are those just directional indicators of where the contact is, or do they represent the direction of the normal force? Yes. Oh my god. Those are the normal directions. Or I suppose not the normal forces, but the direction of the force that the object is applying into another object. It looks really nice. Thank you. Yes, those are the normal directions. Those are the directions that I want to point or apply the force in. Let me restart this. This is a contact collision inspector. I'll go to the other mode where we apply it at a fixed time step. I guess I'll go back to the collision inspector. Okay, so we'll just pull these out of collisions with each other. We have this red box and the green box, and when you see that they overlap, we draw the arrows in the direction that we want to. We have a reference box for the separating axis theorem, the SAT. If you want to understand the geometry behind it, I have it open right here. This is the OBB versus the SAT. Sorry, OBB versus circle. This is the separating axis theorem where you have two boxes. In this case, they're just squares. And you determine the reference box and the incident box. The reference box is the one in which provides the normal that you want to push out of, and the incident box is the box that you want to push out. So in this case, we also color code them in the engine. The reference box has the edge, which is magenta. So the green box is the reference box. It's pushing the incident box out of it. And you can see that's the normal direction at the contact points that we want to apply the velocity in. Yeah, right? So cool. So, and it's working. We spent 2 days ago, we got the separating axis theorem set up on stream. Yesterday we got the clipped points, like figuring out the points on the edges of the boxes that we want to apply the forces in. And today we ported it all into our engine, so now we have pretty much full physics. Full two-dimensional physics finally working. Isn't that so cool? Yeah. So I don't know, the next step is I want to do capsules, but capsule versus line, like specific capsule detection logic was really tricky. And so I can just compose a capsule out of two circles and a square in the middle. And I think before I do that, I had a dream last night where it was kind of like a nightmare, but I was playing a video game, and it was a really shitty zombie video game, and you're driving a car, and like you bump into anything and the car just shuts off and you need to repair it, and zombies are slowly approaching you. And like in the dream, I was just so terrified, and it was just horrible. And I woke up and like, man, I could make something like that in my engine right now. Like I have text, I can load in PNGs, I have a software renderer. I could literally make a game now, like a really shitty simple one, just to test if that idea is actually interesting or not. And I think I'm going to clean up the engine. I'll just leave the physics as is now that it's working like this, and I'll make like a little really shitty top-down game where I'll just have like squares approaching you as the zombies, and I'll figure it out as I go. But I think I can make a really shitty test game over the next few weeks, just to see if that idea works or if I can actually start making stuff with this engine. Because now that we have physics like this, like I can draw stuff, we have physics, that's basically a functional game engine. And I can now start making games in this. So yeah, that's what I have planned next. So yeah, today was very successful. We have full separating axis theorem. We can pull apart oriented bounding boxes. We can push circles out of collisions. Cool. Yeah, it's working. I'm thrilled. I'm absolutely thrilled. This is amazing. I mean, of course, the internal logic of the physics solver. That is a horrific dream, and yeah, that would be really, really cool to see a demo of. Yeah, exactly. Like, I mean, of course, once I woke up, I wrote it all down. I'm like, man, this is just a stupid generic zombie game. But I mean, I don't really like horror games anyway, so I'll just see if I make it and if it freaks me out, and then I can release it, just as a little demo. Yeah, but we have full physics now, like decent physics. I just copied box 2D light and figured out the impulse equation to apply velocities, so we can pull objects apart from each other. So, I mean, of course, this isn't totally original. I mean, I need to learn it from something. So we picked box 2D light, and then we implemented our own collision detection, like the SAT that we got working today. In this stream, you can see me put it together and debug draw everything. There's like 500 lines, but it works. And then we, as a little bonus, we added in circle versus OBB. So yeah, we got physics. We can start working on other stuff now. And I don't know what that'll be, but I think I'm just gonna... The software renderer, like this is all software rendered. So like I zoom in and it starts chugging. You can see the performance down at the bottom. Like we're capping at 60. We're going like over 50 million cycles per frame. Like, so this isn't running at 60 frames per second. This is pretty laggy. So what I would like to do is, like, especially drawing UI over everything, like all this text, all this alpha blended, all these alpha blended UI windows. I think I want to go to hardware rendering now, and I would want to do web GPU. Like there's a native Windows port for it, so that once I get that working, I can figure out how I can make this work in a browser. So I don't need to software render everything. It'll be much faster. Because rendering is why it's so expensive. Like I'm filling in all these pixels every single frame. But I can hardware accelerate it, and then once I have that, I am copping out, and I'm going to use Mini Audio. I downloaded it this morning. After I had the dream, I'm like, okay, I don't have an audio player. I need to find a minimal library that will play audio for me, and it's just one header file. And then I just need to bridge it to the Windows audio playback system, so I could do that, so I could play like a little bit of audio in the game. I get web GPU set up, and then I'll have like a fully functioning game engine that I can start developing a little idea in. So, but since it's all from scratch, except for the audio, I'll have total control of how I want everything to work. So maybe as I set up the really shitty generic zombie game, I'll have interesting ideas along the way, but that's all in the future. I'm just rambling. I'm repeating myself now, but thanks so much for watching, everyone. I am thrilled that we finally have all the collisions that I wanted at this point. So thanks for watching the stream. I'll catch you later. That's it for today. See ya.